going to be using De Moivre's theorem to find the complex roots of complex numbers. And I'm actually going to do an example on this one. And I want to do it for a couple of reasons. First, because this is probably going to be the most useful thing that's going to be learned out of all of this trigonometry material as far as its usefulness for applications in later math, like in Euler's formula, and I guess its uses are pretty much endless, but that is its most important part, is that, well, there's not even much point in talking about it because no one's going to know what I'm talking about. But anyways, it's kind of a big deal. And secondly, because it's going to help me explain where this formula comes from. This is De Moivre's theorem. It's just rearranged. So I feel it's easier just to use the formula, get some answers, and then use those answers to go back and see why they are the way they are. So that's why I'm going to start out with an example. Don't worry, I will explain what all this is doing and where it's coming from and what's going on. It doesn't make much sense to have a formula and not have any idea what's happening with it. So anyways, got a problem. Find the complex roots of minus 1 plus the cube root, or the square root of 3. And I meant to put the cube root here. That's what I meant. So I want to find the cube root of this. So what are its complex roots? Okay, so first thing I need to do is convert this to polar coordinates. So I'm going to find out what the radius is, or the modulus, whatever, same thing. This is equal to 2. Now I'm going to convert these to polar coordinates. Cosine. I'm putting these in degrees because it'll be easier to see the relationship between the different complex roots. But radians are, of course, absolutely fine. I didn't mean to put equals. Okay, so I'm just going to convert this whole thing into polar coordinates. 2. Okay, so I've got this written down in polar coordinates. Now I'm going to talk a little bit about this formula right here. So R is still the same, R is the radius, N is the power of which I'm using. So if I'm taking a square root, N will be equal to 2. If I'm taking a cube root, N will equal to 3. If I'm taking a fourth root, N will equal to 4. Theta is the degrees, so it'll be 120 in this case. And k is equal to n minus 1. And then everything that is smaller than it. So k is equal to 0, 1, 2, all the way to n minus 1. So n for this problem n is equal to 3, so n minus 1 is equal to 2. So I'm going to stop at 2. If n was equal to 4, then I would stop at 3. If n was equal to 5, I would stop at 4. And why this is the way that is, like I said, it's easier to explain once I already have the answer. So I'm just going to go ahead and start using this formula. So k, I'm going to find, let me talk about one more thing. For a cube root, I'm going to have 3 different answers. So if I remember from my earlier algebra, if I have a square root, I could have up to 2 different roots. If I had a cube root, I could have up to 3. If I had a fourth root, I could have up to 4. Well, in the complex plane, it's not could have up to, it is there are. If there's a square root, then there are 2 roots. If there's a cube root, then there are 3 roots. If there are 4, then there are 4. So I'm going to have 3 roots in this case, and like I said, since n minus 1 is equal to 2, for k I'm going to have k0, k1, and k2, so that'll give me 3. So I'm just going to go down the list and start figuring out what these are. So I'm going to start out with z0. Well, first let me just put everything in besides the k stuff, because it's not really confusing or anything like that, but let's just see what it is before the k. So cosine theta, which in this case is 120, divided by n, which is 3, so I'm taking a cube root, plus I, well, let me not get ahead of myself. Let me go ahead and put in the plus 2k pi. So here I've filled out everything except for the k. So now I'm going to do k is equal to 0. I'm going to find out what that is. Then I'm going to do k is equal to 1. I'm going to find out what that is. And I'm going to do k is equal to 2. And I'm going to find out what that is. Once I have all 3 of those answers, each one of those individual k's is a particular root of this complex number, and those will be my answers. And then I'm going to go back and explain why the formula works the way it does and what's going on. So first I'm going to replace z to the k with z0 from this whole formula. z0 2 times k0 pi 3 So 2 times 0, that's going to be 0, so these terms are meaningless. And 120 divided by 3 is 40, so this is a pretty straightforward one. So here is the first root of my complex number. So like I said, I just continue. I go to z is equal to 1 now. I'm just going to write out everything again, just so the formula, well, I'm not going to write out n, but I'm just going to write out the 3, just to remember what the formula looks like. So 2 times 1 now, pi. So 120 divided by 3 is 40, as the same as the last one. 2 pi, I'm going to convert it to degrees. 2 pi is 360 divided by 3 is 120 plus 40, 160. And these both are equal, so I don't really need to do this twice. So z1 is equal to 3 divided by 2, or not, I mean cube root of 3, whatever. This is 160. Remember, I converted this to degrees. 360 divided by 3 is 120 plus 40, 160. So I've got the second one now. And the last one. It's just going to be the same thing, but just z and k is now 2. Cube root of 2. Still 120 over 3. I mean, this is not necessary. I'm just putting it there just to reinforce the what the formula just looks like. Okay. Two times 2 is 4, 360 divided by 320. Oh no, wait, pi divided by, actually I don't need to do it that way. Pi divided by 360 times 240, 40, so 280. Okay, cool. No need to do unnecessary multiplication of annoying numbers. 280, right? Yeah, 40, yeah, 60, 24, 40, yeah, got it. Just wanted to make sure I'd hate to get a wrong number and have to do all this garbage again. And that's my last cube root. So these are the solutions. If I were to put this in my calculator and raise this to the third power, any of these three numbers, put it in my calculator, raise it to the third power, and I should get this one, minus 1 plus cube root of 3i. But anyways, now on to where this formula comes from and why it is the way it is. So let me first off graph what I got here. It's about centered. So the radius is the same for all of these. So r well, actually, let me just start graphing. I don't want to make my graph look ugly. So 40 degrees, that's about, so that's 45 degrees, so that'll probably be something like here. 160 degrees is 180, so minus 20 degrees, so I don't know, it'll probably be like there. And then 280 degrees, 180, 270, so that's probably, go away. That's probably like right there, something like that. And again, the radius is equal to square root of 3 over 2. So this is square root of 3 over 2, this is square root of 3 over 2, this is square root of 3 over 2. Z0, Z1, Z2. Now optically, they look like three equal pieces, and in fact they are exactly equal to each other. So when I take a root, cube root, square root, fourth root, what I'm doing is looking for what I'm looking for is a number times itself 4 times, so 4 equal parts. I'm dividing it essentially into 4 equal parts that multiply to be 1. So they're the same size, but not only that, I can tell that they are the same size because these angles are exactly the same. If I go back up to here, if I take 160 160 minus 40, that's 120. So there's 120 degrees of separation in here. If I take 280 and subtract it by 160, that is also 120. And the difference between 40 degrees and 280 here, at least on a 360 scale, this is also 120. That's not a coincidence at all. It's not even coincidence that my original angle was 120 here. But anyways, that's just to have a picture of it. Now I'm going to go to De Moivre's theorem. So I'm familiar with De Moivre's theorem looking like this. And as I said, it is the exact same thing as this top one. But just for, instead of raising to a power greater than 1, what I'm going to be doing is using it for powers that are between 1 and 0. Which is essentially taking a root or squaring it or fourth rooting it. It's the same thing. So since it's the same operation, I can use the same formula. It's just a different power. It's like multiplication and division. It's the same operation, but optically people set it up differently, or they generally think that there are two different operations, but really what they are is just multiplication. It's both multiplication for division. Division's the same thing. Multiplication, people think, is when you are multiplying something greater than 1 numerically, and division is simply multiplying by something between 1 and 0. So I'm just going to rearrange this since it's the same operation. Now for raising it to a power, I ended up multiplying the angle by however many powers I had. So if n was equal to 2, then I multiply the angle by itself twice. If it was 3, then it would be 3 times the angle. Now, when I'm taking a square root or a cube root, now that I'm taking a root of it, instead of multiplying it, it's going to be divided. And again, it's the same operation is happening, it's just the values of those numbers are going to lie between 1 and 0. So it's going to look like this, even though it's the exact same operation. So now I have pretty much a functional formula of finding a complex root. If I were to use this formula, it would give me one complex root. And in fact, if I compare this to z is equal to 0, that's essentially what I did. Since the k is equal to 0 here, I'm basically just taking my angle and dividing it by theta. And then here's the r, and here's the n, and here's the other n as well. So if I were to ignore this, part, I would already have basically my formula right here. Now, like I said, if I use this formula, it will only give me one of the roots. I would only give me this one right here. I would take 120 degrees and divide it by 3, and it will give me cosine of 40. But I know there are others out there, and what it comes from, so essentially what people did was say z0, I've got something right here. I've got an angle right here. If I spin it around I go all the way around the circle, I land on the same spot, it's the same angle, right? But what have I done when I've gone around in the circle? I've taken theta and I've gone around 2 pi is what I've done. So if I go around 2 pi, this value is the same. So I go around the circle 2 pi times, I arrive at the same spot. So that means every time I add 2 pi, I get the same angle. So I'm trying to think of the best way to explain this. So basically what's happening here is I'm dividing this circle into equal pieces of whatever my angle is, 120. And I want to find out how many times I can divide it and have this space of 120 between. So what I do is I add 2 pi, since theta is equal to theta plus 2 pi, I'm just going to replace theta with 2 pi. So theta plus 2, I don't mean replace theta with 2 pi, I mean replace theta with theta plus 2 pi. And I'll get to the k in just 1 second. Now, the k comes in because I can go around the circle 1 time and it gives me the same angle. I can go around 2 times. I can go 1, 2. So theta plus 4 pi is also equal to just theta. So I can keep adding as many 2 pi's as I want. I can add 2 pi's to my heart's content and it's the exact same thing, right? So I can add 2k pi. So let me just put it in there and hang on a second. I'll explain to you why it's alright. I'll explain about the n minus 1. So I can add 2 pi to my heart's content, add 2 pi, 4 pi, 6 pi, 8 pi, 10 pi. It will always land on z0. It will always be the exact same thing. Now, why do I stop there? So I have this. K is equal to 0, 1, 2, n minus 1. So the reason it goes like in this order, like I said, because I can keep adding as many 2 pi's as I want, and it's going to give me the same angle. This is going to be equal. Now the reason the n minus 1 is in there is because eventually I'm going to get a situation where I've got k over n. So if k is equal to n, then it's going to be equal to 1. So I'm going to end up right back to where I started. So let me just use the example from this problem. I stopped at z is equal to 2. Now if I did z is equal, or z3, let me just show. So cosine 120 over plus 2, 3, pi see what's going to happen. I'm not even going to do the other half. These are going to cancel out, and I'm going to have cosine of 40 plus 2 pi, which is 360, so cosine of 400 degrees. So cosine, so a 400 degrees. So let me go around the circle 360 degrees, and then what do? I go up by 40 degrees. So I'm back at z, exactly z0. So this would be the same. So sine, so this is equal to cosine of 400 plus I sine 400. See, it lands on exactly the same spot. So it doesn't make sense to continue going around the circle. I can continue to go around the circle, but it's going to give me the exact same answer. I can keep adding, I can continue to do as many k's as I like, but after a certain point, after I've gone around the circle one time, then that doesn't make sense to do anymore. Like I said, when k is equal to n, I'm going to get 1, and then I'm going to get no more unique solutions. See, that's why I have the n minus 1, and that's why I stop at, that's why I do k is equal to 0, 1, and 2, because, like I said, every time I add a 2 pi, I'm essentially doing the same angle. But until k is equal to n, I'm going to get unique solutions. So I think that does a pretty decent job of explaining how this formula is working. And like I said, I could technically do a proof, but I don't think anyone would understand it at all, because you have to prove that there are only 3 unique roots, and it's that's something for a different subject. So I don't want to get off topic, but I hope this does a good job to explain it. I know it's a little bit convoluted, but I think you should be okay in understanding this.